Okay, in this part of the video, we're going to discuss the reasons why we want simulation models. Okay, the first reason is very straightforward. It's cheap today. Okay, be careful. It's cheap today, not in the past, because of the widely available computational power. According to Moore's law, number of transistors per square inch on integrated circuits had doubled every year since the integrated circuit was invented. It has been revised to 18 months in 1975. This law tells us that the growth of computational power is fast. There is this exponential growth in computer power. And at the beginning of 20th century, that in that era, we had something called analytical engine. You can consider this as a very ancient form of computer, of PC. And in the middle of 20th century, a computer could be larger than a room. Okay, they used to use a building, a whole building, to contain a PC. And today, I mean, most cell phones, smart cell phones, they are faster than a normal PC maybe 10 years ago. Okay, so computational power today is not that expensive anymore. It's cheap. It's cheap, but still we want more power. We never stop wanting. So today we have even more advanced technologies for computational power. For example, grid computing, parallel computing, cloud computing. But yeah, in one sentence, in summary, today we have the ability, we have the computational power needed for simulation models, because later this semester you will see that even a very simple simulation model could be a big user of your computational resources. Okay, so that's the first reason. The second reason is that some experiments in the real world can be very difficult or impossible to implement. So we want a sandbox on our PC, on our computers, to simulate what is going to happen in the real world, because the real world experiment is not possible. For example, the system no longer exists or is too slow for us to observe. History, anthropology, paleoscience, ecology, geology, all these disciplines, all these sciences, they are studying something does not exist anymore, or something that is changing very slow at a scale of maybe million years. So it's not possible to observe them anymore, or it's just not for us to observe, because as humans we can only live for less than 100 years, right? It's not possible to observe a geology process which could just run in 1 or 2 million years. Some systems cannot be closed, which means that in order to do experiments, most experiments, they require the system to be isolated from surrounding environment. But some systems cannot be isolated. For example, some social experiment. The perfect scenario is that you can just, for example, separate a community or a part of a city from the rest of the world, which is not possible in the real world, right? So in that scenario, you may want to use simulation models to create an isolated environment on your PC, right? And experimenting on the system is unethical. This is due to our moral standards, human society's moral standards. For example, in order to experiment a new educational policy, you may need to withhold educational resources from 50% of school children in a city. So if that's the case, if you want to do this in the real world, the problem is which 50% of school children should be deprived from educational resources. Okay, obviously that's almost an impossible decision for anybody to make because it's unethical, and you cannot tell these children or their families that they have been put into an experiment, and some educational resources have been withheld from them, right? So in that, if that's the case, you may want to do a simulation instead of the real world experiment, right? And there are other experiments that cannot be perfectly implemented or not possible to repeat in the real world. For example, there is a type of experiments is called quasi-experiment. A researcher control, sometimes indirectly assignment to case versus control groups. For example, drug trials, right? We're not experts in medicine, in medical science, but we know that in order to do drug trials, you have to create control group, and there is another group. Control group is people who do not use a new drug, and there is another group for people who are using the new drugs for test, right? Although today drug trials can be very well designed, but they are not perfect. There is always subject intervene in this process. It's not possible to be completely random, and some factors are still difficult to control in a real world quasi experiment like a drug trial. So you may want to use simulation models to carry out very similar experiments in virtual world on your PC, right? And some experiments, they cannot be repeated. And individuals, this type of experiments is called nature experiments. Individuals exposed to the experimental and control conditions are determined by nature or by other factors outside the control of investigators, which means that it's pretty hard to repeat the experiment environment. For example, the lack of aircraft contrails after September 11 of 2001. After the terrible attack, the United States banned almost all the aircraft in the sky for, I think, for 2 weeks or a month. I'm not sure, but we had a very clean sky after 9/11 for at least 10 days. It was something you cannot repeat. Right? You cannot repeat. You cannot just nowadays you cannot simply forbid all aircraft in the sky. Maybe recently because it's because of COVID-19. But again, I just want to say that some experiments, they cannot be repeated. So in order to observe them, in order to find out patterns, you need to use simulation models, right? Simulation models, when we're using simulation models, this type of experiment is called surrogate reasoning, experiment on a representation of the system. Here, when you are using a simulation model, it is a representation of the system. It's not perfect, but it has the components you care about, so you use it to simulate the actual system in the real world, right? Okay, the third reason is that complexity science and nonlinear dynamics, they require simulation models in order to study them. Okay, so complexity science, the study of systems composed of many basic and interacting parts that display organized complexity. And complex systems can exhibit something called emergent behavior. I've mentioned this term before, right? Emergent behavior. It's a type of collective behavior that does not exist on any individual in this system. But when these individuals, they get together, they're following a set of rules. Then suddenly, when you are observing the whole system, there is emergent behavior that cannot be observed on individuals. And the properties of complex systems include past dependence, which means history matters. Okay, and positive feedback, you may have heard this term before, is called butterfly effect. Small effects are magnified. Okay, and self-organization, global order arises from local interactions. Is actually another word to describe emergent behavior. Global order means the behavior that is happening at system level. And it arises from local interactions. It arises from individuals that are following a simple set of rules. Okay, emergence, surprising behavior at the global level, not predictable at the local level. And also, in order to study nonlinear dynamics and chaos, we mentioned them before, right? We need simulation models, right? Linear systems, nonlinear systems, chaotic systems. We mentioned them in the previous videos in mathematical models, right? When I introduced mathematical models. And here is an example of using simulation models to simulate, to represent the real world. It's something called Conway's game of life. It's a type of cellular automata, or in this semester we just simply call it CA. Okay, cellular automata. It's a standard type of spatially explicit model. What is an explicit model? Which means that we know the input and we want to find out output. And the reason why it's called spatially is that Conway's game of life is happening on a grid, or you can consider it's a chessboard. So the format, there must be a two-dimensional grid. Okay, and on this grid, it's fully occupied by a bunch of cells, and each cell is usually a square. Of course, you can use hexagon or other shapes, but you should know that this two-dimensional grid should be fully occupied by cells. There should not be any empty space on this grid. Okay, so usually it's a square. A cell's neighbors are the 8 immediately adjacent orthogonal and diagonal grid cells. So the second sentence here defines something called neighbors. Okay, if there is, you can randomly choose a cell on this two-dimensional grid, and its 8 surrounding cells, they are considered the neighbors of this cell. Later this semester, I'll introduce that there are different ways to define neighbors, to define neighborhood. But for Conway's game of life, okay, surrounding 8 cells, they are all neighbors of the central cell. Cell states are alive or dead. Here, we can smell something about life because we use words such as alive or dead to describe the states of each cell. For alive or dead may not be pretty hard to implement in your PC, but let's just say this: if a cell is alive, it is black. Okay, it is painted black. If it is dead, it is painted white, or you can say it's occupied or unoccupied, black or white, or you can use any other two pairs of colors. But black and white, they are easy to implement in a virtual world, right? Or alive is for 1, dead is for 0, right? Anyway, it's a binary rule here. Okay, there are also transition rules. Birth: a dead cell is born if it has 3 alive neighbors, otherwise it remains dead. Okay, this rule is strict. Okay, survival is also strict. A live cell survives if it has 2 or 3 live neighbors, otherwise it dies. So very simple rules: birth and survival. Okay, a dead cell is born if it has 3 live neighbors. This is just like the real world. Consider that there is a colony. There is a colony, and this colony is spreading out. And there are people in this colony. And if there are enough people, for example, 3 live neighbors, if there are enough people, they will reproduce, right? That's the reason why a dead cell is born if it has enough neighbors. Specifically here, 3 live neighbors, okay? And in order to survive in this colony, in order for this colony to survive, there should not be too many people, because if that's the case, there won't be enough food. Say that. And there can't, in order to survive, there can't be too many people, and there can't be too less people. If there are too less people, nobody is responsible, or not enough people are responsible for finding food or other activities necessary for survival. So it must be 2 or 3 live neighbors. If there are more than 3 live neighbors, a cell will die. If there are less than 2 neighbors for a live cell, it will still die, which means that this colony should not have too many people, either too less people. Okay, so you can say here, I have connected this computer world with the real world, right? That's the reason why it's called Game of Life. It is trying to use simple rules to simulate our real world about giving birth and survival. So here, let me show you the example. Exactly this model in NetLogo. It's model 1.1. It's called life.nlogo. You can just download this library, this package from Carmen. Okay, so this is a model. This is a model. So here you can set the density of living cells. For example, let's just make it 0.41. Set up and go. So you can see all these cells, they're either black or white. Black means alive, white means dead. And they're all following the 2 simple rules I mentioned before, very simple. And at the very beginning, we can say the dynamic, right? A lot of cells, they're either living or dead, but they're changing. But eventually here you can say this system has achieved a very steady state. Some cells, they do not change anymore. They're either black or white. Some of them, they are blinking. We have small blinkers. They are spinning fast, which means that there is still changing happening there. But it's stable. The changing is limited to a specific area, right? Area 1, area 2, 3, 4, 5, 6, 7, 8. And they do not intervene other stable cells, live or dead. So this is how we simulate the real world using very simple rules. Okay, let's just stop this and make the density lower and set up again. Say less alive cells can be seen here because I lowered the density and go. You can say that the system is still running, is still changing dramatically, and I'm not even sure if there is a steady state for this system because this is actually a random simulation model. Yeah, here we go. We have a stable state here, right? Okay, so a Conway's game of life, it's pretty simple. That's the advantage. You only have two rules, and you just assign these rules to every single cell in your world, in your two-dimensional world, and every cell will just go following these rules. And eventually, you can say there is a very complex world running there on this grid. Okay, so Conway's game of life. It was invented by Conway, who was a mathematician, and he died recently due to COVID-19, unfortunately. Okay, and game of life behavior. Let's talk about its behavior. Firstly, it's self-organized. Even when starting with a random arrangement of states, many starting configurations can generate complex global patterns. Okay, here is a wiki page for Conway's game of life. Okay, if you're interested in it, you can go there and there is more detailed information about this model, and it's lifelike. That's the reason why it's called game of life. GOL behaves in ways that can simulate complex biological systems. For example, the fate of any initial configuration is die. Could be die, could become stable or circle with fixed period, could grow indefinitely, could grow and contract in a complex manner. So like I said, these rules, they are simple. But you can use these simple rules to simulate very complex pattern or systems in real world. And there is emergence. The behavior of the system cannot be found in at the individual level rules that drive the simulation. Okay, again, I need to emphasize this: emergent behavior or emergence. It is the core of this course. Okay, at individual level, each individual is following a set of simple rules. Their behaviors can be predicted accurately because they're following rules. But when we're looking at the system from a higher level, from at system level, we can see that there is collective behavior that cannot be explained by the simple rules you just gave to individuals. Each individual is following this simple set of rules, but together they are behaving differently. It's magical, okay? You will see that later. And I also want to mention that cellular automata can also be used in statistics, and it's a very basic form of artificial intelligence. So when we're talking about life, dead cells, live cells, we're playing God. In this small two-dimensional world, we are the God. We gave each agent or each cell in this world a set of rules and let them live. They could die, they could survive, and together they could form colonies, right? Right. So if you look at this method, this tool, cellular automata from this perspective, you are creating intelligent people, right? each cell is, you can consider it as a people. Okay. Okay, I'll just stop here, and I will use another video clip. I think one more will be good enough to finish this chapter. But so far, the most important part is say a cellular automata, and a very simple but very famous, maybe most famous simulation model using cellular automata, which is Conway's game of life. Okay, thank you.